Physiological time series data are one of the most fascinating data structure to work with in machine learning. However, this type of data structure can be hard to work with because of the massive amount of context required to make useful models. From data collection to pre-processing to feature engineering, it can be daunting to play around these information-rich datasets. It's a shame because there's so much open data available for interesting project analysis. In today's video, we'll do a small machine learning project with EEG time series data using Python. We'll classify an EEG segment of 30 seconds from an open data set of participants in a sleep study between awake or sleep. Disclaimer, this analysis is just an overview on how to run a simple machine learning project with physiological data. There's a whole lot more to be done before making it a full-fledged analysis. Let's get started. First, we'll check out the four main building blocks of this whole project. Then we'll take a brief look at the data format we'll be working with, which is called the European Data Format. After that, we'll review the main feature we'll be using, which is called Power Spectral Density, or PSD for short. Finally, we'll take a look at the preferred classification scheme used in machine learning project with physiological data. Let's start with the overview. The first step will be to download the EEG data and put it into a data structure so that we can use it in Python. EEG data is a very complex time series that holds different kinds of information at different frequency bands. We'll check out how to do the filtering to get features for each of these bands later on. After downloading the data, we'll chunk out our very large time series into 30-second epochs that are labeled either awake or asleep. As you can see from the first two rows in this image, we can deduce some kind of difference between the awake stage in green and all of the other sleep stage in blue and red. In the recording, we actually have all the 6 stages labeled, but for our purposes for this analysis, we'll bundle the sleep stage into one megastage. After chunking the data into 30-second epoch, we will then calculate our main feature, which is the power spectral density. The methodology has some intricacy, we'll review it in a bit. Finally, using this power-based feature, we'll train our binary classifier. For this, we'll simply use a random forest classifier. And that's it, that's the flow, fairly straightforward. Let's take a brief look at the EDF data format. If you are curious and want something a bit more in depth for understanding EDF, check out my video on the subject. EDF and EDF Plus are a data format tailored for physiological signal. At the macro level, it's separated into a header with the meta information and a data record section. The format is made to have one file per recording for a patient. You can actually separate the information for recording into multiple files and join them afterward. That's what we'll be doing in the analysis. The header holds info about the patient and technical information about each signal that was recorded. The signals are stored below in the header in the data recording section. Multiple signals can be there and they don't have to be contiguous in time. Finally, you can store annotation and events in the same file, which make it very versatile. Here, you can see some example of the structure for the header and for the data record section. Thankfully, we will be dealing with a library that can handle these type of files easily, so we can load them programmatically without having to worry about the intricacy of the structure. Okay, now on to the main feature that will help us discriminate between asleep or awake. By the way, I found an absolute awesome blog that breaks down the specific feature we'll be leveraging. Do check it out in the description, it's well worth the read. So the power spectral density feature visualized look like this for the Welsh variant. The PSD is defined as the distribution of power across frequency components. So it's really a distribution of what we call power across the different frequencies in the signal. In our case, we don't want all the granular detail on each frequency point basis. We want the average at each of the main frequency bands used normally in EEG analysis. Then we want the delta band in red, average, the theta band in orange, average, alpha band orange and yellow, beta band in green, and gamma band in blue, all of them averaged. The type of power spectral density we'll be using in this short analysis is the multi-taper one. It's usually the preferred method for EEG signal as it helps with handling the noise. There's some intricacy about what are tapers, the taper data, the fast Fourier transform involved, and then the averaging across all of the taper. The details are not too important here for our purposes, but just know that there are 3 general types of ways of calculating PSD with EEG, and that we'll be using the multi-taper one, which is a mix of the previous 2. Finally, let's talk about the classification scheme we'll be using. One thing with physiological data that is important to take into consideration is how much of the data is intimately tied to a person. The emitter of the data is very easily recognizable from the data being gathered. For example, in the study that I published way back, I tested a bunch of EEG headsets on my head across 2 different states. As you can see in the bottom, when I open and close my eyes, I got a very distinct alpha power distribution across my scalp, especially in the posterior part of my brain. This weird distribution is repeated across vastly different headsets and across different recording sessions. With another participant, the distribution will be different. This means that to avoid having a machine learning system learning these quirks between participants and memorizing them, and to focus only on the state to detect, we need to use a leave X subject out cross-validation scheme. The leave X subject out cross-validation scheme is very simple. You train n minus X participant and leave X participant for testing. In the case illustrated on screen, it's a leave one subject out cross-validation. So you train on 2, you test on 1, and then you cycle through all of your participants across each of the fold. This ensures that your machine learning classifier will learn what is generalizable from the participant data, aka what is relevant for the task. For this simple project, we will just train on one participant and test on another one to keep things simple. There are many libraries we can use with EEG data. My particular preference is to use the MNE Python library, which has some very neat APIs. And for the machine learning portion, we'll use the scikit-learn library. Okay, let's jump into the code and see what's up. Okay, here we are in the code. I'm using a Colab notebook. I don't have any need for GPUs in here. It's going to be simple and it's fairly straightforward. There's much more that we can do with the data that I've set up here. But for this particular study, we're going to do a setup here, and we're going to just do the step for 2 participants and 1 recording session for a binary state. And then the step 1 will be loading data and pre-process it. Step 2, feature calculation. Step 3, classification. Finally, we're going to analyze the result. And we're going to constrain the problem so that it's way simpler, just so that we can go from point A to point B easily. Okay, so let's look at the setup. First off, we need to install MNE because it's not actually something that is native for Colab or whatnot. You actually have to install it. Okay, and now it's installed. So the next stuff that we need to add here, we're going to import MNE and something called fetch data to actually fetch this specific data set that we're going to use. And we're going to use matplotlib, numpy, and scikit-learn here at the end. The data is coming from this study from like a while ago, 1995. It's age-gendered affect different characteristic of slow wave in the sleep EEG. The data is available for this particular study in the Physionet database. You can check it out. There's a lot of data freely open source here that you can download and start analyzing. So we're going to make use of this. Okay, and finally for our setup here, the experiment variable that we need is first the actual classification target. It's going to be awake, which is going to be 1, sleeping, which is going to be 2 here. And the second thing that we have here are the frequency bands. So we have delta, theta, alpha, sigma, and beta. So these will be the frequency bands which we're going to filter the data with and which we're going to then calculate the PSD on. Loading the data and pre-processing, this is now the next step. So the way to load data and to pre-process, I've bundled everything into this particular function here, load data, which take the ID of a participant and this thing, the event ID here, so that we can create our epoch properly. There's a lot of intricacy here, but this is how we're calling it. We're calling load data with the participant ID, and then we're going to return a tuple of raw training information. So this is the EDF loaded. This is some event information for debugging purposes. And this is actually the important point, which is the epoch training, which will contain the epoch of data and the label, so the X and Y together. As you can see here, we're going to use participant 0 for the training and participant 1 for the testing. So let's take a look at the load data function now. What we have in the data set actually is 6 different stages. We have the stage W, which is wakefulness. We have stage 1, 2, 3, 4, and then the stage R, which is rapid eye movement. And what I'm doing right now with this is I'm setting this stage to 1 and all of the other stage to the label 2, which is what we need here to match the awake and sleeping stage. So what we're going to do is we're going to convert these annotation of the different sleep stage into that annotation over here. So remember the function that we used that we got from the library at the start is fetch data here, and then we say what do we want to fetch. There's many different parameters here, but basically what we have is we're saying which recording session we want. There's multiple. Here we're just taking one, and we're taking one participant at a time. We get the participant file. This is like the file that are downloaded into our file structure over here, right? It's going to be downloaded actually. It will be downloaded over there in the root section. We're going to see it in a few. And once we have that, right, the raw data, we're going to load it into a data structure here. And we're going to use the read raw EDF function from MNE. And it will take a bunch of stuff, but basically what it's going to do is going to read the header and then the signal and structure them so we can put them there. There's two files in each of the participants for the specific data. Let's take a look at them. Okay, so if you see here in the MNE data section, we have PhysioNet sleep data, and we just downloaded two participant data. So the participant 0 and 1. And you see here, this one is for the participant 0. This one is for participant 1. We have two things. We have the polysomnographic data here and the hypnogram. So this is the label and the event, and this is the actual data. But these two are EDF that represent the same session. Okay, so after that we have read annotation, which is reading the second file. So this one is read over here with participant file 0 to get the raw EDF. Here it's read from the first file. And after that, what we're going to do is we're going to do some processing before combining the two, so that in the raw EDF we have one thing which has annotation in it, right? What we're doing here is just cropping, because in this data set there was a lot of information recording on the wakefulness stage before and after the onset of sleep. So what we're doing here is just keeping 4 hours of wakefulness event before and after the sleep session, just so we can balance out roughly the wakefulness versus the sleep stages here for our classification. After that, we chunk the data into 30-second epoch by using the MNE events from annotation. So we're going to get events here, and we're going to then feed these events into the epoch constructor. Over here, we're going to feed the raw EDF, the events, the event ID we want to match with this event, and then like how long this event should, how long this epoch should be. It should be roughly 30 seconds, right? But I'm actually doing 30 seconds minus 1 divided by the signal frequency here, just to avoid some of the bugs that can happen when you have like exact 30 seconds, especially at the end of the recording section. So that's roughly what's happening. It's just a bunch of pre-processing here. Because of MNE Python, there's a lot of stuff we don't have to do because it's properly handled by the library. Really cool one, check it out. Okay, so if we look at the data we have here, we have the raw training here. There's a whole bunch of stuff that we're not using. There's two EEG that we're going to be using, but there's also EOG, a respiration channel, a EMG, a temperature, all that jazz. We're not using that. And if you look at the epoch train, you see we're roughly 30 seconds. There's 548 awake epoch of 30 seconds and 653 sleeping epoch. So that's what we have right now. And finally, let's actually plot all of this stuff. So this is the first channel. We have the FPZ-CZ, and we have the PZ-OZ here. A bit different. We see different waveform. There's all of this other stuff that we're not using at all. And then there's the event marker that represent all of the different 6 possible classes that we have. Anyway, so what we're gonna work with is mainly this. We're gonna filter that out and leverage that thing. If we look at the distribution for the participant 0 here, between the sleeping and the awake, we have here the awake just before, and then we have the sleeping here. The participant kind of awake throughout, right? Not that much, but it does. And then after that, we have that. So this will classify, these epoch will classify as awake, these epoch also, and these epoch will classify as sleeping. The hardest one will be these one to classify, I believe. So if we do a simple plot here of the PSD, right, just to visualize it across the 2 specific stage. For participant 0, we have this power spectral density plot, and then we have for the sleep stage something else in orange. We see there's major difference between the two here, and that the difference is a bit different in different participant, but it's kind of looking the same. There's like this bump here that is there at about, I don't know, 15 here, same thing here. So if we are able to kind of get the feature that help us here, we'll be good to go. Same thing for this gap that we have. The difference is important. At the earliest here, maybe not so much discriminative, but these two should be discriminative. So now that we've went through loading the data, let's take a look at the feature calculation. You're going to see it's not that complicated with M&E. So here's the actual feature we're going to have. We're going to calculate EEG power bands here. We're going to give it an epochs, like a bunch of epochs, and it will calculate whatever we need on the spectrum for each of the frequency bands here. So it will calculate everything that we need for a whole vector of epochs. So let's go step by step. First, what we do here is we compute the power spectral density on the EEG channel, right? So there's going to be 2 channels. We're going to calculate with this minimum frequency and this maximum frequency. So we stop at 30 here, and then we're going to get the data out of it, which is all of the power spectral densities and the frequencies. So we're going to do some normalization here, right? So that will help across all of the different epochs that we have before calculating like the actual average features that we need. And the shape of the PSDs will be like this. So we have all of the epochs. We have the number of channel here. We have 2, right? Because we have 2 EEG channel. And then we have all of the frequency bins. And then what we're going to do here is we're going to reshape our stuff so that we have epoch. And then here we're going to have 10 features. We're going to have 10 features because we have 2 channel, EEG channel, and then we have 5 average bands. Remember, here the frequency bins is from 0.5 to 30, and there's a lot of them. But we don't need all of this granular information, that much feature. We can average out to get only like the delta, theta, alpha, beta, gamma bands. So here we have the X input feature that will be empty, and this is what we're going to return at the end here. And how it works here is that we're gonna end up with like 5 5 frequency bands, sorry, 2 different EEG channel, and the number of epochs, not essentially that number, but it will be somewhere around here. And then we're gonna concatenate that so that we're gonna get like the epochs times that quantity. So how we do that is we go through the frequency bands. So these ones that we defined way at the top with the min and the max here. Right, we go through these. We have the F min, F max. We're gonna slice through the data over here, calculate the mean across this axis here, the last one, and then we're gonna have our power spectral density average across band for all of the epochs. And this is what we're going to add to the X for each of the bands. And then we're going to reshuffle. So that's what we're going to do here. So basically what we do, compute the spectrogram by default is the multi-tapper. And then we're going to normalize. And then we're going to average. That's in a nutshell what we're doing here. Pretty simple. So the step 3 here is to do the classification. So before that, we're going to actually define what is random here. What I did here is I sorted the event, so basically like awake and sleeping, and then I defined what is a random guess based on the number of epoch and like how much of this stage happened. So for the training participant, so randomness is like close to 54%. So like if you were just to say 1 all the time, you're gonna get like 45% accuracy. If you're gonna say sleeping all the time, you're gonna get 54. It's a bit different for the test participant. You see, awake 35%, sleeping 64. So just baseline, if you were just making a classifier that said sleeping, it would be better than random guess of flipping a coin and whatnot. So just to keep these in mind for the rest of the classification afterward. So our step here, we're gonna use a pipeline from scikit-learn here. We're going to use the function transformer, and we're going to give the EEG power band a feature function that we have here. And since we have an X, this is content as a transformer, and then it will take the raw data that we give, the epochs, feed it into here, and then give it to the random classifier, which has a predict function. So then it will be actually training here with these parameters. So the X that we get out of here will go over there. And that way we're training here is there's no complicated cross-validation, because remember, we're training on participation 0, we're testing on participation 1. So we're going to take the epoch train, and then we get all the events so that we can get the Y train over here, and then we're going to do X and then Y, and this X is actually the epochs, which will go through this transformer that will give us the X. So we're fitting here, and we're not tweaking any hyperparameter in this particular case because we don't have a cross validation loop. We're just using like some base parameters. After that, we're doing the predict here with the Y pred, and then we're gonna get an accuracy score. This fairly straightforward, nothing too complicated. What we get now when we shoot this out there, we get an accuracy score of about 86%, which is better than 20% better than if we were just having a dumb sleeping classifier. So that's this. So this whole process we did before to prepare the data accumulated here with a few lines of code to actually do the modeling. If you look at the result in a bit more depth, we have our precision here, our recall. What is actually happening is that sleeping is always easy to detect. So we have our true label being 2, predicted label being 2 here. What we have a tendency of over saying that is actually sleeping, which makes sense given the density of the data. This awake stage was actually under predicted. With more data, would we be able to have a better classifier? For sure. Should we use more of the participant? Of course. And then should we use more feature? Absolutely. I think we should use the other signal of the feature in order to make something good. But with this, we get from point A to point B easily. And also don't forget here, sleeping is like 5 different stages cram into one, and REM stage and the other sleep 1 to 4 stage are kind of vastly different than between the REM stage and the awake stage. So there's also this to take into consideration. But that's it. That's the whole flow from start to finish of a sleep stage classification using EEG data. All right, I hope this was useful. Don't forget to like the video if it was the case, and leave a comment if you have any question. I'm here to help. Have a great week, everyone, and see you in the next video.